Hi, I'm Will Dangler, and this is the 6th episode of The Art of Math Proof. I'm very excited to make today's episode because today we are going to be proving that an integer cannot be both even and odd, and in order to do so, we're going to need to learn a new proof technique. We're going to need to learn how to prove things by contradiction, and that just happens to be my favorite way to prove things. So, how can we show that an integer cannot be both even and odd? Well, so far in this series, we proved 3 things, and those 3 things were all very similar. We proved that the sum of 2 even and the sum of 2 odd integers was always going to be an even integer. We've also shown that the sum of an even and an odd integer was going to be an odd integer. Now, if you recall, each of these proofs were very similar. They started off with us assuming we had 2 integers of the correct even and oddness that we needed. For instance, in this proof that the sum of 2 even integers was going to be even, we assumed we had 2 even integers. In the sum of 2 odd, we assumed we had 2 odd integers. And finally, in the sum of an even and an odd integer, we assumed we had an even and an odd integer. And then using those assumptions, we were able to take our definitions of even and oddness along with our rules of algebra and show directly that the sums of these integers, these even and odd integers, was in fact always going to match the definition of even or oddness. And therefore we completed our proofs. Now these proofs were very easy. That was the point. That's why they were in the first episodes. Now today's proof, it's a little different. We're proving that an integer cannot be both even and odd. So before we were showing that if some properties exist, then some other property must be true. And today we're stating that, well, there can't be such a thing that has these properties. It's a fundamentally different type of thing that we're trying to show. So how on earth do we show that an integer cannot be both even and odd? And how do we make that argument apply to every single integer? Well, that's quite the tall order. So if we're going to show that any integer cannot be both even and odd, then we should be able to take a single integer and go through and show that it must be either explicitly even or explicitly odd and not both. Well, of course, this won't be a proof because it's just a single example, and we would have an infinite number of examples to go through in order to prove that no integer could be both even and odd. We can still take the time to look at a single example and see if we can gain some knowledge there. After all, if it is going to be the case that no such integer can be both even and odd, then it better be the case that for some integer we choose that it can't be both even and odd. So let's make sure that this statement isn't complete baloney. Let's choose an integer and examine why it cannot be both even and odd. Let's choose the integer 1. Well, we know that the integer 1 is an odd integer. We know that based off our definition of oddness, because we said an integer is odd. There exists a second integer such that the first is equal to twice the value of the second plus 1. And of course, 1 is equal to twice the value of 0 plus 1. Or 1 is equal to 2 times 0 plus 1. And therefore, 1 is odd by our definition of oddness. So can 1 be even? Well, what would it mean for 1 to be even? Well, 1 is even if there exists a second integer such that 1 is equal to twice the value of that second integer. 1 is even. There exists a second integer such that 1 is equal to twice the value of that second integer. So we need to show that this second integer cannot possibly exist. Well, how do we know that this integer k, cannot exist and therefore 1 cannot be even? Well, we know that the even integers are the multiples of 2. So let's look at what multiples of 2 are around 1. Maybe we're missing something. Maybe there is an integer k that we can multiply by 2 to get 1. So what are the multiples of 2 around 1? Well, there's 0, which is 2 times 0, and 2, which is 2 times 1, and there's negative 2, which is 2 times negative 1. And we can write those out. 2 times 1. And we get that is less than 0, which is 2 times 0, which is less than 2, which is equal to 2 times 1. So if 1 is going to be even, there needs to exist some integer we can multiply by 2 to get 1. But looking at our multiples of 2 near 1, it doesn't look like such an integer exists. After all, we go from negative 1 to get negative 2, and we 0. We're getting closer to 1, but we're at 0. 2 times 0, we're still not at 1. And then the next multiple, 1, 2 times 1, takes us to 2, which is past 1. We're now beyond 1. So at least in these 3 examples, we can say for sure that none of these could possibly be the second integer. Negative 1, 0, and 1 could not be the second integer. We multiply by 2 to get 1. Furthermore, we know that if we were to multiply any negative integer by 2, any one whatsoever, we're always going to get a negative integer. And therefore, no negative integer that we multiply by 2 could possibly equal 1, because 1 is not negative. So we just eliminated every single negative integer from being our possibility for k. So if k does exist, we know that it is non-negative. Well, we know that k is also not 0 because 2 times 0 is 0. So we now know that if k exists, it has to be positive. Well, we know that k can't be 1 because 2 times 1 is 2, which is greater than 1. So therefore, k has to be strictly greater than 1. But if we multiply any integer greater than 1 by 2, we're going to end up with an integer greater than 2, which is of course greater than 1. And therefore, no integer we multiply by 2 that is greater than 1 could possibly equal 1. Well, that means we've eliminated the negative integers, we've eliminated 0, we eliminated 1, and we eliminated every integer greater than 1 for a possibility for k. But that is every single integer. And therefore, we know that k cannot exist. And thus, 1 cannot be even. But we know that 1 is odd. So therefore, we've shown for at least this one example that it's impossible for 1 to be even. However, we do know that it is, in fact, odd. Okay, well, that was a little tedious. It took some time to show that just for a single integer, that it has to be the case that it cannot be both even and odd. So how are we going to come up with this argument that can apply to every possible integer? And why do we even need to? Isn't it, of course, the case that an integer cannot be both even and odd? Didn't we base our definition of oddness off of what it meant to be even? Didn't we say that an integer was odd if it's equal to an even integer plus 1? Well, that's how we developed our understanding of what it meant to be odd. But at the end of the day, the definition we came up with oddness, that there existed a second integer such that the first is twice the value of the second plus 1, has nothing to do with evenness. Our definition of oddness is completely independent of evenness. And similarly, our definition of evenness, that there exists a second integer such that the first is equal to twice the value of the second, is completely independent of our definition of oddness. Now, I'm not saying that the two ideas are completely independent of one another. I'm saying that the way we have written them, the way we have chosen to define evenness and oddness, has made them independent of one another. We do not yet know if there is any formal relationship between even and odd integers. For us to know, we need to prove things about that relationship, and that is exactly what we're doing. We're making our first call today. We're showing that an integer cannot be both even and odd. We're relating even and oddness, but our definitions do not actually do so. Okay, well, how on earth are we going to show that for every integer, it cannot be both even and odd? Let's think about how we did our last proofs. As we recapped earlier, the first thing we did was we assumed we had an integer that was even, or we assumed we had two even integers when we needed to prove that the sum of two even integers was going to be even, or assumed two odd integers, or assumed an even and an odd integer. But today we need an integer that cannot be both even and odd. Well, what if I want to assume that I have an integer that is even and odd? What? I have an integer that is even and odd? Well, we're trying to explicitly prove that an integer cannot be both even and odd, so how on earth can you assume that you have an integer that is both even and odd? Well, I didn't say my assumption was correct. In fact, my entire argument, the entire argument that we together will make today, will be based around this assumption, and we will show that everything falls apart because we make this assumption, and therefore we'll know that our assumption has to be wrong. And if our assumption is that we have just any arbitrary integer and it is both even and odd, and we show that that assumption is wrong, that assumption cannot possibly be true, well then we will have proven that an integer cannot be both even and odd. So how on earth do we show that this assumption is incorrect? How do you work with something that can't possibly exist? How do you even assume you have both an even and an odd integer? Well, what if we assume we had this even and odd integer and then simply use our definitions of even and oddness and our properties of algebra, as we did in our previous proofs, to explore what else we know must be true? And what if in those explorations we ended up stumbling upon something that we know cannot possibly be true, but would have to be true because we made our assumption? We are going to go searching, hunting for a logical fallacy, some sort of absurdity that we can look at and say, no, that is not true, and the only reason we got that it was true was because we made this original assumption, and therefore that original assumption might be false. So, and today in particular, to show that an integer cannot be both even and odd, we're going to assume we have an integer that is both even and odd. And as a result of that assumption, we are going to show that the integer 1 would have to be even. But hold on a minute. We just showed that the integer 1 cannot possibly be even. It is odd, it can only be odd, it can never be even. And therefore, that is a logical absurdity. So, if we do assume that we have an integer that is both even and odd, and as a result of that assumption, we show that 1 must be even, which we know is impossible, then we know our assumption is incorrect. And therefore, we know that no integer could be both even and odd. Because if there was one, then 1 would have to be even, which we know can't be true. So let's get started. Let us actually assume we have an integer that is both even and odd. We'll call it n. So we're going to assume the integer n is both even and odd. Okay, well, since we're assuming n is even, then we know that by the definition of evenness, there is going to exist a second integer that we can multiply by 2 to get n. Let's call that integer j. So because n is even, we know that there exists an integer j such that n is equal to 2 times j for some integer j. Okay, well, not only is n even, but n is also odd, and by the definition of oddness, we know that there exists some integer k, such that n is going to be equal to twice the value of k plus 1. So we can write that down. So n is going to equal to 2k plus 1 for some integer k. Well, okay, if n is equal to both 2j and n is equal to 2k plus 1, well then that means that 2j is equal to 2k plus 1 because they're both just different ways of describing it. So we can write that 2j is equal to 2k plus 1. Okay, well then we know that we can subtract 2k from n on both sides of this equation, and we'll still be following the properties of algebra because after all, n minus 2k is equal to n minus 2k, even if we write them in these other forms. So let's do that subtraction now. And that will result in us having 2j minus 2k is equal to 1. But what is minus 2k? Well, we took the time last episode to define subtraction in terms of addition. We said that subtraction was defined to be the difference of two integers, x and y, was defined to be x plus the additive inverse of y. So therefore 2j minus 2k is really the same as 2j plus 2 times negative k, or 2 times minus k. So this we can convert to a problem of addition. Okay, so now we have that 1 is equal to 2 times j plus 2 times minus k. But wait a minute, 2 times j is an even integer, and 2 times minus k is also an even integer. But if we're adding together two even integers, we're gonna get another even integer. After all, that was the very first thing we proved in this series. And as such, since we have 1 written as the sum of two even integers, it must be the case that 1 is even. But wait a minute, we said that 1 can't possibly be even. 1 has to be odd. So, we're done. We've reached our contradiction. We've shown that 1 would have to be even if we had some integer n that was both even and odd. Okay, well, that was pretty fast. You didn't really do much. Well, let's slow down. A lot just happened. Let's look at what we did. So we wanted to show that no such integer could exist where that integer was even and odd. In order to do so, we assumed we had that very integer. And then after that assumption, we simply followed our definitions and our rules of algebra and facts we knew from previous proofs. And in doing so, we arrived at the fact that 1 would have to be even, which we know is impossible. So if we were to go from the bottom of this proof and backtrack up to where we made a mistake, we will find that our mistake was made in our assumption that n was both even and odd, and therefore our assumption was incorrect. So let's backtrack now. Well, we said 1 is even because it's equal to 2 times minus k plus 2 times j, which are both even integers, and we noted that we've already proved that the sum of two even integers is always going to be an even integer. So that was that was valid. There's no mistake made there. Okay, well, how did we get here? Well, we got here because we said that 2j minus 2k was equal to 1. So we converted this problem of subtraction into a problem of addition. But this was valid as well because we followed our definition of subtraction. We didn't make a mistake, so okay, this step is also fine. Well, how did we arrive here? Well, we arrived here because we realized that, well, n is of course equal to n, and we were able to substitute in the values for n. Where we said n was 2j, so we could write that on one side, and n is also equal to 2k plus 1, so we could write that on each side. And then once we had done so, we were like, well, n minus 2k is going to be equal to n minus 2k. And yeah, that's of course true. And so the way we arrived at this step was also valid. Furthermore, this step right here, where we wrote 2j equal to 2k plus 1, we know is valid because we were simply substituting in the values of n. Finally, we got that n was equal to 2j and n was equal to 2k plus 1 in the first place because we said n was even, and this is simply matching our definition of evenness. We said n was odd, and this simply matches our definition of oddness, so no mistake there. Finally, taking us back to our assumption. We assumed that n is both even and odd. And that's no rule of algebra, that's no thing we've previously proven, that's an assumption. And turns out it's an incorrect assumption because by doing so, we get that 1 is even, which we know is impossible. And therefore, we have proven by contradiction that no such integer could exist if it was both even and odd. So this concludes today's episode. In the next episode, we're going to take the time to look at some similar or equivalent definitions for what it means to be both even and odd. Well, not at the same time. Anyways, this has been Will Dangler. Till next time.